Hi there. We're going to talk about radioactivity today. This is Phychem 2 of Unit 9. We have three key ideas that we're going to be looking at. What happens when an element undergoes radioactive decay? How does radiation affect the nucleus of an unstable isotope? And how do scientists predict when an atom will undergo radioactive decay? Alright, so starting to look at our first question. So after radioactive decay occurs, the element changes into a different isotope of the same element or into an entirely different element. So it depends on the type of decay that takes place. So radioactive decay is defined as the disintegration of an unstable atomic nucleus into one or more different nucleotides. So disintegration is just breakdown, so just a fancy word for breakdown. Nuclear radiation is the next definition. Particles that are released from the nucleus during radioactive decay. There are different types of nuclear radiation. They can contain things like alpha particles, beta particles, gamma rays, and neutrons. We're going to look at a few of these in turn. So when we talk about alpha particles, an alpha particle has the same mass as a helium atom. So we tend to show a helium atom here, and it affects the decay such that the atomic number changes by a unit of 2, and the mass changes by a unit of 4, which ends up being the same as this helium. So we call this an alpha particle. We've got a relative mass here. Charge is +2, and we tend to show a graphic showing the 2 protons, 2 neutrons. Beta particle only affects the atomic number, so it does not affect the mass. We'll talk about these symbols later, but the top number is going to be the mass, the bottom number is the atomic number, and then we have a symbol here, E, to show electrons. We can see that this number is smaller because it has a larger negative exponent, so this is a much smaller mass than the alpha particle. It can have a charge of -1 or +1, and we just show usually a blue sphere to indicate an electron. A gamma ray, we use the Greek letter gamma. It doesn't have a mass because it's more of a wavelength, more of a radiation that takes place. It does not have a charge, so we tend to show this wavy line as gamma rays are being expelled or coming off. A neutron only affects the mass, it does not affect the atomic number. And it has a little bit less, it's a little bit lighter than this alpha particle, but not much. Has no charge, and we tend to use the silver or more of a white sphere to indicate a neutron. Alright. So alpha particles consist of protons and neutrons. We can define alpha particle as a positively charged particle that consists of 2 protons and 2 neutrons that is emitted from the nucleus during radioactive decay. We'll look at these here in a little bit as far as what they actually look like and how they affect other substances. A beta particle, these are electrons produced from neutron decay. So we can define a beta particle as an electron or a positron that's emitted from a nucleus during radioactive decay. And then gamma rays are high energy electromagnetic radiation, so electromagnetic waves. Define gamma ray as a high energy photon emitted by the nucleus during fission and radioactive decay, and we'll talk about fission and fusion in the next section. But fission is just the combining or joining of two elements. Neutron is radioactivity occurs in an unstable nucleus. So neutron emission consists of matter that is emitted from an unstable nucleus. Neutrons don't have a charge. Neutrons are able to travel farther through matter than either alpha or beta particles. So able to penetrate more deeply is another way to think of that. Nuclear decay. So how does radiation affect the nucleus of an unstable isotope? Anytime that an unstable nucleus emits alpha or beta particles, the number of protons or neutrons, those are affected. So nuclear decay equations are similar to those used for chemical reactions, and we'll get to those here shortly. A gamma decay changes the energy of the nucleus, so there's no charge in the atomic number or the atomic mass of an element. The atomic number changes during beta decay. The mass number before and after the decay does not change. The atomic number of the product nucleus increases by 1, and the atom changes to a different element. Alright, beta decay process occurs when carbon-14 decays to nitrogen-14 by emitting a beta particle. So here we've got a nuclear equation that we're showing. Carbon-14 emits this beta particle. Note it does not affect the mass, so the mass is still 14, but our atomic number is 1 less. I'm sorry, 1 more. So if we did the math on the right side of this equation, 7 minus 1 gives us 6, right? So if we're going the other way, if we have 6, we know beta particles emitted, what's remaining then? So 6 plus 1 then. We do a little algebra, add 1 to both sides, and then that gives us 7. Or another way to look at this, 7 plus a minus 1 gives us 6. Okay, both atomic mass and number change in alpha decay. Atomic mass decreases by 4, atomic number decreases by 2. So if we have radium-226, it's written as follows. So radium-226 has atomic number 88. If it's emitting an alpha particle, well, 226 minus 4 gives us 222. 88 minus 2 gives us 86. So we have to look at the periodic table when our atomic number changes, and we have to look up element 86, and we can see that it's radon looking at the periodic table. Alright, so we've got a math scale here, looking at a nuclear decay reaction. So we have actinium-217 decays by releasing an alpha particle. We're going to write the equation for its decay process and determine which element is formed. So we're going to write the equation down. The original element's on the left side, so we have AC as the element symbol. It's 217. We have to look at the periodic table to figure out the 89 part, the atomic number. So if we know AC, though, we can find 89 as the atomic number of the periodic table. It's going through a decay process, and we're told up here it releases an alpha particle, so we know the alpha particle's there. So we have to figure out what this substance is, and we've got some information here. X is the unknown product, or the element symbol. A is the unknown mass, the mass we want to find, and Z is the unknown atomic number, or the atomic number that we want to find. So if we do some math, 217 equals A plus 4, so we're just looking at the top part of the equation, 217, A and 4, and then we'll look at the bottom, 89, Z and 2. So that's what we have here. We arrange the equations so that we're solving for A. So subtract 4 from both sides, so 217 minus 4 gives us a new mass of 213. So we're going to write that here. And then Z, rearrange, so subtract 2 to both sides, 89 minus 2 is 87. That's our new atomic number. So looking at the periodic table, element 87 is francium. So that's our new element. Alright, radioactive decay rates is the next thing we're looking at. So how do scientists predict when an atom will undergo radioactive decay? So one thing we want to note, it's impossible to predict the moment when any particular nucleus will decay. But it is possible to predict the time required for half of the nuclei in a given radioactive sample to decay. So we call this half-life. This is the time required for half of a sample of radioactive isotope to break down by radioactive decay to form the daughter isotope. So half-life is a measure of how quickly a substance decays. And we've got several applications where we can use half-life. Doctors use isotopes with short half-lives to help diagnose medical problems. With short half-life, it breaks down quickly in the body and the body can get rid of it. Scientists can also use half-life to predict how old an object is. Geologists calculate the age of rocks. by using half-life of long-lasting isotopes such as potassium-40. We can also use something called carbon-14 that is present in anything that was once living up to a certain age. To a certain age, the amount is so small that it's hard to really quantify or get a value for. And I think I mentioned carbon-14 here in a little bit. But let's say that we've got a half-life problem. We've got radium-226. It's got a really long half-life, 1,599 years. So how long will 7/8 of a sample of radium take to decay? So we've got two givens. We've got half-life is 1,599 years. Our fraction of sample decayed is 7/8. So we want to know the fraction that remains and then how long the decay process takes place. So we're going to calculate the fraction of radioactive sample remaining first, and we just take and assume that we had 1 or 100% at the beginning, decayed 7/8. So what's remaining? 1 minus 7/8, or 8/8 minus 7/8 gives us 1/8 that is remaining from the sample. So remember that we can convert 1 into whatever fraction we want to. So we want the denominator to be 8, so we're going to have 8 over 8, and that's going to be 1 to give us 1/8. So we want to then determine how much of the sample is remaining after each half-life. So after one half-life, half of the sample remains. 2 half-lives, well, we have 2 halves, and we multiply those fractions together, we get 1/4 of the sample remains. And how much is remaining after 3 half-lives? Well, half times half times half gives us 1/8 of the substance remains. And then if we had 4, we could multiply by another half, or 5. Just keep multiplying by halves here to give us the value that we want. So each half-life lasts 1,599 years. Our total time to get to 1/8, right, because we had 8 that we wanted. So there's 3 half-lives here. So that's what we're multiplying by. So 3 times 1,599 gives us 4,797 years. So this is the total time required for this decay to take place. Long time. So radioactive decay is an exponential decay, and we'll talk about a decay curve, or we'll show you a decay curve here in just a second. This is just the graph of a number of radioactive parent nuclei that remain in a sample as a function of time. It is a logarithmic relationship, which you really don't have to worry about. And then carbon-14, as I mentioned before, the ratio of carbon-14 to carbon-12 decreases with time in non-living organisms, but we can compare this ratio in a living plant or animal, and then we can estimate how long ago once living organisms had passed or had died. So it just decreases over time. So here's this decay curve that I was talking about, and it's just a logarithmic function. But you'll notice that the curve is decreased. So up here at the top left corner, we've got 100% of our sample. And then at the bottom, we've got half-lives. So how many half-lives? So after one half-life, we've got half of our sample that remains. 2 half-lives, we've got a 1/4, and then so on. So the amount of substance that we have, or the fraction, is going to continue to decrease. But notice how this line is sloped. And this line is going to get closer and closer to 0. But it's never going to get to 0 because it's this logarithmic or curved path. But it might get to the point where it's so small that we're not really able to actually measure how much sample is there, or how old a sample was. So it only works for a certain given period of time. So thanks for listening.